In this STR8CHEM session, we're going to learn how to write the integrated rates equation for zero order, first and second. And this is only limited for a single reactant reaction. We're going to look at zero order first. So let's consider a reaction with the hypothetical reactant A to make products. So A can be any kind of reactant to be making any kind of products. For zero order, the rate can be written as rate equals to K. Remember, K is the rate constant times the concentration of your reactant A to the power of 0. So anything that will be to the power of 0 is going to be equals to 1. Thus, for the reaction here, when it is a zero order reaction, the rate will be equal to K. When you look at the rate law over here for zero order reaction, we can say that the reaction rate is not affected by the concentration of reactant. So no matter how much you're going to add or you're going to take out the reactant right there, the rates of the reaction will be the same before or after the change on the concentration of your reactant. So the graph of rates versus the concentration of your reactant will look like this. So it will not going to be affected by the changing of the concentration of your reactant. That is zero order. So what about the integrated rates equation for zero order reaction? We have looked at the rate law. Remember, this is how you're going to write the rate law. Please go back to the video in which you have learned how to write the rate law before you're going to watch this video. So for the integrated rates equation for zero order would be written like this. So you have concentration of the reactant in the beginning when you have concentration A, and then you have subscripted 0 right there. This is the initial reactant, the initial concentration of the reactant, minus the concentration of the reactant after a given time. So you have initial concentration of the reactant minus the concentration of the reactant after a given time equals to K. K is the rate constant times with T, which is the time given. And the units for zero order reaction would be molar per second. This is the units for the rate constant. If you have a question that is asking you about a certain order of reaction, if you look at the rate constant units, and whenever you see this, this is the indication that the reaction is a zero order reaction. So when you rearrange that, you would get something like this. Okay, so when you rearrange the integrated rates equation over here, you get something like this. This looks really familiar. So when you relate this with the y equals to mx plus c, the rearrangement that you have right now is a formula for a straight line. So the straight line over here will have the gradient, negative gradient, which is m equals to negative k right over here. And you have the initial concentration would be C, and then Y is equals to the concentration of A at a given time. So when you transfer that into the axis over here, for that axis, you're going to have the concentration of A at a given time. And then the axis right there would be your time. So since you have gradient, remember m is the gradient. So this part over here is the gradient, and the gradient is a negative slope. Therefore, the line would be looking something like this. Okay? So that slope over there is m equals to negative k. So that is the slope. And then this point right there is your C value, which is going to be the initial concentration of the reactant. Now next, let's have a look at the first order reaction. We're going to consider the same type of reaction. Remember, we're only going to be talking about single reactant reaction. Over here, we have hypothetical reactant A to be producing products. So for first order reaction, the rate law will be written in this form. You have rate equals to K, and the concentration of your reactant over here will be to the power of 1. So this is the rate law, okay? Remember? So I'm just gonna highlight that. So that is the rate law, just like what we have talked about for zero order reaction just now. And if you look at the relationship between rates and the concentration of your reactant, we can say that the reaction rate is directly proportional to the concentration of reactant. Thus, the graph for rates versus concentration over here, we will be having a directly proportional relationship, okay, for first order reaction. So it's slightly different from what we have for zero order just now, which is for zero order reaction, the concentration of the reactant will not gonna be influencing or affecting the rates for zero order. But for first order reaction, the concentration of the reactant will be changing the rates. So when you have more reactant, you will have higher rates. If you have little reactant, you will have slower or lower rates. Now let's have a look at the integrated rates equation for first order reaction. How does it look like? It looks quite similar to the zero order reaction integrated rates equation. The only difference over here is you're going to have ln in front of your initial concentration of the reactant minus ln the concentration of the reactant at a given time. Okay, so when you look at the integrated rates equation for the first order reaction, it looks quite similar to what we have for the zero order. The difference over here, you have ln and ln right there. Okay. Another difference is when you look at the units of rate constant, so that is the rate constant K. So the units for K for first order reaction will be per second. Okay, it's different from what we had for zero order just now, which is molar per second. For first order, we have per second. When we rearrange the integrated rates equation for a first order reaction, if you rearrange that to get a straight line equation, you have this equation right here. So I am just rearranging that to be looking like the y. This is your gradient, x plus c. Again, when you look at the slope over here, it's a negative slope. Okay. And when you look at the y-interception, it's going to be ln concentration A initial. And the y-axis is going to be ln concentration of A at a given time. So when you try to complete the linear graph for first order, for that axis right here, you're going to write ln concentration A at a given time versus time. And the shape will look like this for the straight line. Again, that is the slope, negative slope, and that point over here is your y-interception. What about second order reaction? So we're going to consider again the same single reactant reaction A to be making products. For second order reaction, the rate law looks like this. Okay, rate equals to K, rate constant K, times concentration of your reactant to the power of 2. Because this is second order reaction. So we can say that the reaction rate has exponential relationship with the concentration of the reactant. Okay? So what you have now, instead of a straight line, you have a curve like this. Because this one is to the power of 2. Okay? The rate versus concentration graph will have a curve shape. So what about the integrated rate equation for second order reaction? So for the second order reaction, it will look like this. It's slightly different from what you have seen for zero and first order just now. You have 1 over concentration at a given time minus 1 over concentration initial equals to K times T. And the units of K is also different, which is per molar per second. So when we rearrange the integrated rates equation to get a straight line equation, you will have the equation to be looking like this. Therefore, this is your y. You have your mx plus c. When you look at the slope, now you have a positive slope. Okay? And when you look at your y-interception, it's right there. And the y-axis is right over here. Right. So when we complete the linear graph for second order reaction, your y-axis will be 1 over concentration A, T. And over here will be time. You will have a positive slope. So that is m equals to k. M is the gradient, remember? Okay, so you have, that is the slope. And that point right there is your y-interception, which is 1 over concentration A initial.